If you find your website too boring, try this. In this video, we'll use JavaScript to create an interactive 3D website with a model that moves with each scroll. I believe this will be the easiest tutorial you've ever seen on this topic, because we'll go from the most basic steps to completing a real 3D product. After watching this video, you'll be able to build your own 3D experiences. Let's get started. First, we need to prepare a small website. This is its current interface, but you can use any website you like. Now let's access Sketch tab to search for 3D models. When searching, remember to click the filters for downloads and animations. Choose a model you like, then click Download. Note that you must select the GLB format. That's it. We now have our 3D model. Returning to the project, I need to create an element with the ID space -3D. This is where we'll display the 3D space on the screen. Next, I need to create a JavaScript file to write our code. Remember to import it as a module. And that's all we need to prepare. With JavaScript, I need to import the Three.js library to work with 3D models, and GLTF loader to read model files in GLB format. To work with a 3D model, we can divide the process into two main parts. The first part is the 3D space, where we place objects such as the model and lighting. The second part is the camera, which is the determining factor in what we see. For example, the camera will have a wide 45-degree field of view. The aspect ratio will match the screen size of the device, and the viewing range will be from 0.1 to 1,000 meters. By default, the camera is positioned right in the center of the coordinate axis, so I will intentionally move the camera 5 meters away along the Z-axis to get a wider view. So have we seen the 3D model? No. The camera and the scene are just tools. The image captured by the camera is what we can actually see. I'll call it the renderer. This image will be sized to fit the device's screen. Now we just need to render the scene through the camera. After we have the image, we'll insert it into the HTML element we prepared earlier. Use getElementById to access that element, and append child to add it. Now scroll to the bottom of the page and you'll see a black area. This is the 3D space that has been created. By default, its background will be black. To make it transparent, simply set the alpha value to true. First, I will create a variable to store the model. Then I will use GLTF loader to read the model file that we downloaded. Once the model is loaded, it will be available inside the file scene. After retrieving the model, we can add it to our 3D scene and render the scene again to update the image on the screen. I created a mixer variable to control the animation, and the object being controlled is our model. Now, let's go back to the model loading page we looked at earlier. In the animation section, you'll see a list of all the animations included in the model. In my case, there is only one animation, called Take 001. Depending on the model you choose, there may be several different animations available. Now, let's return to JavaScript. Here I search for the animation named Take 001. If the animation is found, the animation controller will select that animation and play it. We've declared everything, so why isn't the animation working yet? Let's imagine it this way. Every movement in the real world is created by continuously displaying a sequence of frames. When we run the animation, it only plays the first frame. So our job is to continuously move through all the frames in sequence. That's what creates the illusion of movement. To do that, I'll create an animate function. Inside this function, I'll use requestAnimationFrame to continuously repeat this process. Each time the function runs, I'll update the animation so it can move forward to the next frame. The larger the value passed into mixer.update, the faster the animation moves forward. Then we'll render the scene again to display the latest frame on the screen. Now it should work. At the moment, I think the animation is moving a little too fast. So I'll reduce the value passed into update to slow it down. The reason we see the model as black is because it hasn't been illuminated yet. In 3D space, there are two types of light. The first type is directional light, similar to sunlight. Here the sunlight is white with an intensity of 5. The higher the intensity, the brighter the light. Once we have the light, we add it to the scene. By positioning the sunlight 5 meters along the x-axis and 5 meters along the y-axis, the parts of the model facing the light will receive direct illumination and appear brighter, while the parts that don't receive direct light will appear darker. And that's why we need a second type of light. The second type of light is primary light, which is non-directional and illuminates the space evenly. Therefore, even areas not directly exposed to sunlight will have a soft glow instead of appearing dark. After we've declared the lighting, we'll add it to the scene. In 3D space, the 3 coordinate axes, X, Y, and Z, are fixed. In theory, we only need to change the model's position directly. However, writing the code here might not work because the model hasn't finished loading yet. So for testing, I'll place the code inside the callback where the model has already been loaded. Now, I'll change the x-axis value. A positive value moves the model to the right, while a negative value moves it to the left. Similarly, changing the y-axis value moves the model up or down. For the z-axis, a larger value moves the model closer to the camera, while a smaller value moves it further away. However, if we assign the position directly like this, the model will instantly jump to the target position. It does move, but there is no smooth transition or animation. Instead of directly changing the position value, I will create a target variable to store the position I want the model to move to. For example, let's say I want the model to move to x equals 1, y equals 1, and z equals 1. Inside the animate function, I will use Three.js lerp function to gradually move the current x value toward the target x value. The third value, 0.05, is the interpolation factor. It controls how much the current value moves toward the target on each frame. The x position will gradually increase or decrease until it approaches the target value. A larger interpolation factor makes the movement faster, while a smaller factor makes the transition slower. Similarly, I will use the same method to change the position of the y-axis and z-axis of the model. From now on, whenever we need to change the model's position, we just need to change the value of the target position variable, and the animation effect will be performed automatically. Similarly, each model can also rotate along 3 axes. I will also add the target values of the 3 axes to the variable target in the animate function. I will also increase the x-axis rotation value from the initial value to the target value with a conversion factor of 0.05. It's exactly the same as how we moved slowly before. So we will continue to replace the y-axis and z-axis rotation values to save you time. But there's a problem. The default rotation axis value is a number, which is quite confusing, right? So let's use the dg to rad function, with the value being the number of degrees you want to rotate. This will help us convert the value from degrees to numbers so it can work. For example, I want to buy a model that rotates 90 degrees or 45 degrees. So from now on, when we want the model to move or rotate, we just need to change the value of the target variable. In this project, I've already created several large content blocks. The first block is called tab 1, followed by tab 2, tab 3, and finally space 3D, where our 3D model is displayed. Because I want the 3D model to stay fixed on the screen while we scroll through the page, I'll do the following in CSS. First, I'll set position : fixed so the 3D model stays in the same position on the screen. Then, I'll set all 4 edges to 0 pixels using inset 0. However, there's one problem. Because the 3D model is positioned on top of the page, it could block our interaction with the content underneath. So remember to add pointer-events : non-semicolon. This allows the mouse to pass through the 3D model, so we can still interact with the content below. Now using JavaScript, we need to create a variable called tabs to store the tabs we want to monitor. In this case, we'll include tab 1, tab 2, and tab 3. Then, we'll loop through each tab and use Intersection Observer to check its position relative to the viewport. The threshold is set to 0.5, which means the callback will be triggered when at least 50% of the tab is visible on the screen. If you want the animation to start earlier, you can reduce this value. Once the condition is met, we can continue checking which tab is currently visible. For example, if the current tab is tab 1, we simply get the corresponding target values and update the position we want the model to move to. In tab 1, I want this dragonfly to land on the branch, so I'll move it slightly to the right along the x-axis. Then I'll lower it along the y-axis to bring it closer to the branch. Next, I'll increase the z-axis value to move it closer to the camera, which will make it appear larger. Finally, I'll rotate it 90 degrees around the y-axis so that it faces to the left. So what happens if the current element is not tab 1? Then we'll continue checking to see whether it's tab 2. If it is, we'll update the corresponding position and rotation values in the target variables. In this case, I want the model to move to the left, so I'll decrease the x-axis value. Then I'll increase the y-axis value to make it fly a little higher. I'll also increase the z-axis value to bring it closer to the camera. Finally, I'll rotate it 90 degrees around the y-axis so that it faces the left side of the screen. And that's it. Most of the code is repeated. For each different tab, we simply change the position and rotation values to create the movement we want. So let's continue with the last tab, tab 3. In tab 3, I want the dragonfly to move closer to this bush. Just like we did with tab 1 and tab 2, we simply adjust the X, Y, and Z position values until the model reaches the position we want. I'll rotate it 90 degrees around the X-axis. Now the dragonfly appears to bow its head down toward the bush. It's an interesting idea, but I don't really like the result, so I'll set it back to 0. Of course, these choices depend on your own sense of aesthetics. If you like, you can adjust the model from different angles to create a look that stands out more. From now on, every time we scroll the page, the browser will check which tab is currently visible. Based on the current tab, it will update the position and rotation of the 3D model using the values stored in our target variables. This allows the model to smoothly move from one position to another as we scroll through the page. And that's how we create the scrolling animation effect. Since we know that making the model move only requires changing the values in the target variables, we can make it react to other events as well. For example, in tab 1, I've added a button. My goal is to make the model move when I hover over this button. In JavaScript, I'll first select the button using getElementById. Then, I'll use addEventListener to listen for events on it. The first event is mouse enter, which is triggered when the user moves the mouse over the button. Because I only want to change the model's x-axis position, I don't need to update all the other values. I'll simply decrease the x value, causing the model to move to the left. As you can see, when I hover over the button, the model moves toward it. However, it stays there even after I move the mouse away. So we need to listen for another event, mouse leave. This event is triggered when the mouse leaves the button. At that point, I'll simply restore the x-axis value to its original position, allowing the model to return to the branch. Similarly, you can listen for other events that fit your design and use them to create even more special effects. Actually, there's a problem we haven't noticed yet. When setting up the 3D environment, we set the width and height of the space, as well as the camera's aspect ratio, to match the width and height of the display screen at that time. Of course, that's correct. But if the user changes the browser window size while using the application, the 3D space will no longer fit the new screen size. That's why we need to listen for the event that occurs whenever the browser window is resized. When that happens, we'll update the size of the 3D space to match the new browser window size. At the same time, we'll update the camera's aspect ratio to match the new screen dimensions. Finally, we'll call the update projection matrix function to apply the new aspect ratio. From now on, even if the screen size changes, the 3D space will automatically adjust to fit the current display screen. So in this video, I've shown you how to set up a 3D model, lighting, and a camera, as well as how to control animations, make the model move in response to events like mouse movement and hovering. and make the 3D environment responsive to different screen sizes. If you found this video interesting and helpful, don't forget to like and subscribe to the channel for more interesting videos. And if you have any questions or requests for the next video, feel free to leave a comment below. I'll do my best to answer them as soon as possible. Now, that's all for this video. Goodbye, everyone, and I'll see you in the next one.